So let's talk about how to interface an ultrasonic sensor to a Raspberry Pi 4. So ultrasonic sensor is used for distance measurement and gives fairly accurate readings as it's using ultrasonic sound to find the distance. So this is an ultrasonic sensor, as you can see. It has two eyes like this. One end is labeled R here, one is labeled T, that's the transmitting, this is the receiving end, and this is a pinout, 4 pinout. That's the ground, echo, trigger, and a VCC. So this is what we're going to be using. This is the ultrasonic sensor. It is used to detect obstacles or read the distance between where it is to where an obstacle is. So it can be accurately used for measuring distance in the range of 2 cm to 400 cm with an accuracy of 3 mm. So there are 4 pins on the ultrasound module that are connected to the Raspberry. VCC to pin 2, ground to pin 6, trigger to pin 12. So we're going to be connecting it based on this. So we'll now see how to measure the distance of an object using HCS R04. So this is the spec of the ultrasonic sensor that we're working with. So ultrasonic sensor, in order to send a 40 kHz ultrasound, the trigger pin of the sensor must be held high for a minimum duration of 10 microseconds. After this, the ultrasonic transmitter will transmit a burst of 8 pulses of ultrasound at 40 kHz. Immediately, the control circuit in the sensor will change the state of the echo pin to a high. This pin stays high until the ultrasonic hits an object and returns to the ultrasonic receiver. So the echo pin remains high until it hits an obstacle, and then the signal is echoed back. That's when the echo pin becomes a low. So based on the time for which the echo pin stays high, you can calculate the distance between the sensor and the object. For example, if we calculate the time for which echo is high as 58 microseconds, then you can calculate the distance with the help of the speed of sound, which is equal to 340 milliseconds. So this is a formula for calculating the distance. We're going to apply this in our program, in our code. So the formula says that distance is equal to velocity of sound divided by time over 2. So we are dividing time by 2. We are taking average of time here because the time value here is a total time of the time it takes to be transmitted to the obstacle and the time it takes to reflect back after hitting the obstacle. So we're going to take an average of it here. So this is the value. Now the velocity of sound in air standardly is 340 milliseconds. That's what we're using, 340 milliseconds here. So when you divide it by 588 microseconds, at the end of the day you have 10 cm when you convert it. So this is the circuit diagram we're going to be working with. If you look at this diagram very well, you can see that we have two resistors here, 330 ohms and 470 ohms here from the echo pin. Remember, initially I told you that the GPIO pins of the Raspberry Pi cannot withstand a voltage above 3.3 volts. So because of that, since we expect a high to be returning from the sensor back to the Raspberry Pi, which is at 5 volt level, we need to use two resistors as a divider here to reduce the voltage to approximately something around that falls in the range of 1.8 to 3.3 volts. So when you do your calculation using these two values, you're going to get 2.9 volts here. So this is what we are going to be doing right now, and this is the program we'll be writing. So let's first of all run our connection, and then we will also look at our program. So let's connect the diagram. So the first thing here is I'm going to connect my ground. So I'll be using black for ground. So this is my ground. So I'll put it in the top end here. That's the ground. Then the next thing I'm going to do is to connect my 5 volts. So my 5 volts, this is my 5 volts here. So this is our 5 volts. So the next thing I'm going to do is to connect my trigger point. Remember, we are following this diagram here. So the trigger point is going to be going straight up to GPIO. What? This should be, let's look for it. 1, 2, 3, 4, 5, 6. So we'll go to our pin out here. 1, 2, 3, 4, 5, 6. It was GPIO 18. So we're going to be using GPIO 18. So I'm going to put it at GPIO 18, which is at the 6th point. So we'll have 1, 2, 3, 4, 5, 6. So the last thing that remains to be connected is our resistor. So I've already used 3 resistors here. Each of them is 1K. So using these values is going to work for you. So you have 1K versus 2K, 1K versus 2K. So the top here is going to be the 1K. So 1K goes to our echo. While this other end goes to the ground. So we have a ground pin here. Then the middle here, middle of our resistor, this is it, is going to GPIO. Let's find it. It's going to 1, 2, 3, 4, 5, GPIO 12. So don't forget that. So we are using 12, and we're also using 8 here. So I'm going to take it to 12. So GPIO 12. So we are ready. That's it here. So the next thing we are meant to do is to write our program. Don't forget the pins that we are working with. Don't forget the pins that we are working with. Don't forget the pins. So I'm going to kind of minimize this so we can see directly. Now our trigger pin goes to this point, which is GPI 18. Sorry, GPI 18 here. So GPI 18 goes to our echo trigger pin. Then GPIO 12. So 18 and 12 are what we're working with. So let's go straight to the program. So we're working with 18 and 12. Please do not forget that. Now let's write a program that will do that. So Control A, Control C, Control N, then we'll paste. I don't need this anymore. So the program we're going to be using, in fact, I think I should just copy this. So this is the program we're going to be working with. Okay, we can't really copy this way. Yeah, so for us to be able to copy this way, you may have to use a different interface. So I'm going to use terminal. So let's create a file called ultrasonic.py. So inside it, I'm going to paste it. So if you're using nano file this way, you can easily paste. So I'm going to paste it, then Control X to save, Y, enter. So let's run it. Python ultrasonic.py. So can you see that we are beginning to get values? 185 cm, 196.1. So when I obstruct it, I'm getting 9.5, 9.6, 9.4. You can see that. So that's it. Very easy. Very easy. Very easy. So I'm going to terminate the program by pressing Ctrl C to terminate. So let's go back to our nano here and then copy Okay, so let me explain the code once again. So first of all, we are going to import our GPIO pins. Secondly, we are going to import time library. Then we are going to set GPIO.setMode to BCM numbering format. Then our GPIO pins, we are going to set 18 to be our trigger point, our echo pin to be 12. Then the next thing is our setup. So our trigger pin becomes our output, our echo becomes our input pin. Then we have a function here called distance. So this function here called distance is where we're going to first of all send a 40 kilohertz through our trigger pin, and then when it echoes we're able to capture the time. So GPIO.output trigger through, you're sending a high to trigger pin here. Remember, trigger pin here has been made to be 18. Okay, so 18 comma through. So you're sending a high to it. Then you're gonna wait for 10 microseconds. This 10 microseconds. Then you send a 0 to the same trigger pin. Then you make sure you're picking the current time of start and the current time of stop. I mean the time when the signal goes out. So you're expecting it to echo back. So you remain here. There's a while loop here. So while GPIO.input echo is equal to 0, so it's going to remain here as far as the echo pin is 0. You know, it's going to capture the start time. Then at this point, when the echo pin becomes a high, it's going to now capture the stop time. Then it's going to calculate. Can you see time elapsed here? It will now be stop time minus start time. That will give us the time it took for it to transmit and then echo back. So the distance is now the time elapsed times 34,300 cm per second divided by 2. So divided by 2, we are dividing time by 2, remember? So that's it. Then we return distance. So this is actually where the program starts. So if name equal to main, try except. So what is it going to try? Y always true. Capture your distance. It's going to call the distance function here. Pass when it returns the value of distance. dist here picks up the value of distance. Then it's going to print it out using this measure distance is equal to %.1f. This is formatting. So it's another way of formatting string. So it's going to just pass in this value called dist here in place of percentage here, and then print it out for you in 1 decimal places because you have .1. If you put .2 here, you're going to have 2 decimal places. Then this is going to actually stop whenever you interrupt the keyboard by pressing Ctrl C. So that's what interrupts the program. So GPIO.cleanup is going to make sure that all configurations that you've done before concerning your pins are all cleaned up. And that's the last end of the program. So the program is actually very easy and simple. So I believe that this is very interesting. So you can try it again. You can see the values we're getting at terminal. The more I move further, the more the distance increases. When I come closer, the distance goes towards 0. So that's exactly how to work with an ultrasonic sensor using the Raspberry Pi 4. Thank you.